Now in this lecture we'll answer two questions. In the first question we find out the radius of this circle that blocks quadrilateral ABCD, and in the second question we find out the length of this line segment AP that is equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have quadrilateral ABCD that is described by this circle. You know that AC is the diameter of this circle. You also know that AB equals to AC. You know that the perimeter of this quadrilateral ABCD equals to 18 units. That is to say, the sum of its side lengths is equals to 18 units. AB plus BC plus D, AB plus BC plus CD plus DA equals to 18. And you also know that the area of this quadrilateral ABCD is equal to 16 square units in its size. Again, our task is to find out the radius of this circle that blocks quadrilateral ABCD. Okay, so first of all, we define the side lengths of this quadrilateral ABCD with letters. We define the length of side AB as A. AB equals to BC in its length, therefore BC must be also equal to A. We define the length of side AD of quadrilateral ABCD as B. We define the length of side CD of quadrilateral ABCD as C. So in the next step, we will implement Rule 7 in our drawing. So let's click on Rule 7. According to Rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. This is peripheral angle ACB that subtends on chord AB. That is the diameter of the circle, and therefore it is equal to 90 degrees in its size. So according to this Rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So we can implement Rule 7 in our drawing. For input in our drawing, we have this is peripheral angle ABC that subtends on chord AC, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size according to Rule 7. Likewise, this is peripheral angle ADC that also subtends on the same chord called AC, that is the diameter of this circle, and therefore it must be equal to 90 degrees in its size according to Rule 7. In the next step, we implement the Pythagoras theorem on those four right triangles. We implement the Pythagoras theorem on this right triangle ABC and on this right triangle ADC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is a variation of Pythagoras theorem. in this right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, in this right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so electricity, so it is AC squared equals to AB squared. AB is 8, therefore AB squared is 8 squared plus BC squared. BC is also 8, so BC squared is 8 squared. So in total, I should remember that AC squared equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared. Going to question 1. So in the next step, we represent the Pythagoras theorem on the right triangle ADC. So according to the Pythagoras theorem, on this right triangle ADC, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. Again, according to the Pythagoras theorem, in the right triangle ADC, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. AC is the missing side, so electricity, so AC squared equals to AD squared. AD is B, therefore AD squared is B squared plus DC squared. BC is C, therefore DC is C, therefore DC squared is C squared. So in total, according to equation 2, we can find out that AC squared equals to B squared plus C squared. While according to equation 1, we only found out that AC squared equals to 2A squared. So we have two different equations for AC squared. Therefore, we get equation 3 that states that AC squared, according to equation 1, must be equal to AC squared, according to equation 2. AC squared, according to equation 1, equals to 2A squared, and it must be equal to AC squared, according to equation 2. AC squared, according to equation 2, equals to B squared plus C squared. So in total, according to equation 3, I should find out that 2A squared equals to B squared plus C squared. So here we divide this equation 3 by 2, and finally get that according to equation 3, A squared equals to B squared plus C squared over 2. This gives us the equation that the perimeter of this quadrilateral ABCD is equal to 18 units. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is A, CD is C, and DA is B. So in total, A plus A is 2A, 2A plus B plus C equals to 18. also it is also given us the question that the area of this polygonal ABCD equals to 16 square units in its size. Polygonal ABCD consists of those two right angles. Therefore, the area of polygonal ABCD in total is equal to the sum of the areas of those two shapes that it consists of. So the area of polygonal ABCD in total must be equal to the area of the first shape that it consists of, the area of this right angle ABC, plus the area of this second shape that is consists of, the area of this right angle ADC. And again, the area of polygonal ABCD must be equal to the sum of the areas of those two shapes that it consists of. The first shape is triangle ABC, so it is the area of the first shape that is the area of triangle ABC, plus the area of the second shape, that is the area of the right triangle ADC. It is given as a question that the area of polygonal ABC equals to 16 square units in its size. So we substitute the area of polygonal ABCD by 16. And it is equals to the area of the right triangle ABC. What is the area of this right triangle ABC? The area of the right triangle ABC equals to the base AB times the height BC over 2. AB is A, BC is A, divided by 2. So it is A times A over 2, that is A square over 2. So in total, the area of the right triangle ABC equals to A square over 2 square units in its size. Plus the area of the second shape that's polygonal ABCD consists of, the area of this right triangle ADC. The area of this right triangle ADC equals to the base AD, that is B times the height DC, that is C over 2. So it is B times C over 2. So the area of the second shape that polygonal ABCD consists of is B times C over 2 square units in its size. So in total, we should found out that 16 equals to A square over 2 plus BC over 2. Here we multiply the equation 5 by 2. Finding again that according to equation 5, 16 times 2 is 32 equals to A square over 2 times 2 is A square plus BC over 2 times 2 is BC. So in total, we actually found out that 32 equals to A square plus BC. And again, according to equation 5, 32 equals to A square plus BC. But according to equation 3, we only found out that A square equals to B square plus C square over 2. And again, according to equation 5, 32 equals to A square plus BC. And according to equation 3, A square equals to B square plus C square over 2. So, we substitute A square in this equation 5 by B square plus C square over 2 from equation 3. So according to equation 5, 32 equals to A square according to equation 3 is B square plus C square over 2 plus BC. So in total, according to equation 5, we found out that 32 equals to B square plus C square over 2 plus BC. So here we multiply BC by 2 and then we divide it by 2 in order to account factor of this expression. And we get that according to equation 5, 32 equals to b squared plus c squared over 2. We have 2 times bc, we have to multiply bc by 2, so it is 2 times bc divided by 2. We multiply it by 2 and then divide it by 2, so we change nothing. So in total, we should have known that 32 equals to b squared plus c squared plus 2 times b times c over 2. Here we multiply this equation 5 by 2. And finally we get that 32 times 2 is 64 equals to b squared plus c squared plus 2 times b times c. So here we use the algebraic identity. Let's say that a squared plus b squared plus 2 times a times b equals to a plus b squared. So according to this algebraic identity, we get a squared plus b squared plus 2 times a times b equals to a plus b squared. According to this algebraic identity, we get that b squared plus c squared plus 2 times b times c equals to b plus c squared. And it equals to 64. So in total, according to equation 5, we actually found out that b plus c squared equals to 64. Here we take out all those equations. And finally we get that b plus c squared, the root of b plus c squared is b plus c equals to the square root of 64 is 8. In total, according to equation 5, we actually found out that b plus c equals to 8. This is according to equation 5. But according to equation 4, we only found out that 2a plus b plus c equals to 18. And because of the fact that b plus c equals to 8, let's have that b plus c this equation 4 by 8. We do it now and get it according to equation 4. 2a and b plus c is 8 plus 8 equals to 18. According to equation 4, 2a plus 8 equals to 18. Here we subtract 8 from this equation and equation 4 and finally we get that according to equation 4, 2a equals to 18 minus 8 is 10. So 2a equals to 10. Here we divide this equation 4 by 2 and finally we get that according to equation 4, a equals to 8 over, a equals to 10 over 2, that is 5. A equals to 5 minutes in its length. So this is side AB is equals to A and A equals to 5, therefore AB equals to 5 of course. Likewise, this is side BC is also equals to A and A equals to 5, therefore BC also equals to 5. So in the next step, we implement the Pythagoras theorem on this line ABC. This right triangle ABC according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, in this right triangle ABC according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so we have to see this, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25, plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So total AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. Here we substitute 50 by 25 times 2 and get that AC squared equals to 25 times 2. Here we take out all those equations and get that AC equals to the square root of 25, that is 5, so inside the root we left only with 2. In total, if you know that AC equals to 5 times square root of 2 units in inside. AC is the diameter of this circle, is equals to 5 times square root of 2 units in its length. Therefore, when you find the radius of this circle is R, the radius R must be equal to half of the diameter. That is the radius that we are looking for. So the radius R must be equal to the diameter AC over 2. The diameter AC is 5 times square root of 2. So if you divide it by 2, you get the radius. So the radius R, that is the radius that we are looking for, the radius R of the circle equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, is equal to 3.536 units in its length. And then let's solve the first question. I repeat again, if you found out that the radius that we are looking for in this question, that is the radius of this circle, equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, the radius of this circle R equals to 3.536 units in its length. So we finish with the first question. The next step, I present you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the length of this line segment AP, that is equals to x. We have to find out the value of x. So, in the drawing, we have a circle that is inscribed by this right triangle ABC. Repeat again, in the drawing we have a circle that is inscribed by this right triangle ABC. This is angle ABC, that is the right angle. You know that the line segment QS equals to 25 units in its length. This is called QP. This is equals to 24 units in its length. This is a tangent, that is tangent to this circle to this point, so we define the point of tendency of this tangent with this circle. This point is point M. So SM is a tangent to the circle at point M. Again, our task is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So first of all, we implement rule 2 in our drawing. So repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing, we have a circle. This is the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule 2, they are equal to each other. That is to say, the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common standpoint point A, from this common standpoint point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ, but AP equals to X. Therefore, AQ must be also equal to X units in itself. In the next step, we will define the length of tangent, the short tangent BM, this tangent BM, SA. And we focus on this common standpoint point B. From this common standpoint point B, we have tangent BM and tangent BQ. According to rule 2, they are equal to each other. That is to say, BM equals to BQ, but BM equals to A, therefore BQ must be also equal to A units in its length, according to rule 2. SM is a tangent to the circle at point M. So SM is a tangent, it is absolutely straight line. So if we focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have on the upper side of the straight line SM at point B? We have this angle that is equal to 90 degrees. Plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we focus on this common standpoint point S. From the common standpoint point S, we have tangent SM, that is tangent to this circle at point M. Likewise, this is called PQ, the extended called PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10 in our drawing. So if we click on rule 10, rule 10 is true in any circle, so in any circle, if AB is any chord in the circle and PT is a tangent to the circle, then the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So in the drawing, we have a circle. This is the common standpoint point P. From this common standpoint point P, we have tangent PT, that is tangent to the circle at point T. Likewise, the extended chord VA touches point P. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can implement rule 10 in our drawing. In our drawing, we have the common standpoint point S. From the common standpoint point S, we have tangent SM, that is tangent to the circle at point M. Likewise, the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true, that SM square equals to SQ times SP. Again, SM square equals to SQ times SP. So now, And then again, according to rule 10, the following equation is true. That SM squared equals to SQ times SP. SM is the missing tangent, so we leave this it is, so it is SM squared equals to SQ times SP. SQ is 25 and SP equals to SQ plus QP. SQ is 25, QP is 24. So in total SP equals to 25 plus 24, that is 49. And again, SM squared equals to SQ times SP. SM is the missing side, so it is, so it is SM squared equals to SQ, that is 25, times SP, that is 49. Here we take out all those equations and find again that the missing tangent SM is equal to the square root of 25, that is 5, times the square root of 49, that is 7. So in total SM equals to 5 times 7, that is 45. SM equals to 5 times 7, that is 35. So the length of tangent SM is 35 units. This is tangent SM, the length of this tangent SM is 35 units. What is the length of this mission 97 SB? SB equals to SM minus BM. Again, SB equals to SM minus BM. So it is known. So SB equals to SM minus BM. So SB in total equals to SM, that is 35, minus BM, that is 8. So in total SB equals to 35 minus units in itself. In the next step, we will implement the Pythagoras theorem on this side diagram SQB. So we implement the Pythagoras theorem on this green right diagram SQB. According to the Pythagoras theorem, on this green right diagram SQB, QS squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. And again, according to the Pythagoras theorem, this is again triangle SQB. SQ squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. QS is 25, therefore QS squared is 25 squared, that is 625. and it is equals to qb square. qb is 8, therefore qb square is a square plus bs square. bs is 35 minus a, therefore bs square is 35 minus a square. So in total, we found out that 625 equals to a square plus 35 minus a square. So 625 equals to a square plus 35 minus a square. 35 minus a square equals to 35 squared, that is 1225 plus a square minus 45 times 8, that is minus 78. So in total, we should know that 625 equals to a square plus 1225 plus a square minus 78. So 625 equals to a square plus a square is 2a square, and we have minus 78 plus 1225. So here we subtract 625 from this equation. If I get it in this side of the equation, we left with nothing, that is to say 0. While on the other side of the equation, we have 2a squared minus 78. 1225 minus 625 is 600, so it is plus 600. So here we divide this equation by 2. And finally we get that 2a squared over 2 is a squared. 138 over 2 is 135a. And 600 over 2 is 300. 0 over 2 is 0. So in total, if you don't know that a squared minus 45a plus 300 equals to 0. So this is the quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared plus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 45a plus 300 equals to 0, the variable that we are looking for is a. So x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 45. And finally, the coefficient c equals to 300. So we have all the data that is needed in order to find out the value that we occur for this specific quadratic equation, that is a. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way, we find out the value or the values of a, because a is the variable that we're looking for. In our specific quadratic equation, therefore x equals to a. So here x equals to a, so this is x by a, and it is equals to minus b. B is minus 45, therefore minus b is minus 45, that is plus 45, plus minus square root of b square. B is 135, therefore b square is 135 squared, that is 1225. 1 4 times a times c. A is 1, c is 300, so 1 4 times a times c is 1 4 times 1 times 300, that is 1200. Over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, let's found out that a equals to 35 plus 1 square root of 1225 plus 1200 over 2. So a equals to 35 plus minus. Inside the root we have 1225 plus 1200 is 25 divided by 2. The square root of 25 is 5, so in total we found out that a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40 and 40 over 2 is 20. So the first solution for a is that a equals to 20. And the second solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 30 and 30 over 2 is 15. So the second solution for a is 15 and the first solution for a is 20. This is the red triangle PQA. The red triangle PQA is an associated triangle called side AQ equals to side AP. And QP is of course the best of this grand associated triangle in QP. So in the next step we do a construction, that is to say from point A we go perpendicular to the base QP. Again, from point A we go perpendicular to the base QP. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When you find the touching point of the perpendicular from point A in the base QP, this point is point Z. So we have here an associated triangle, and from the base A, and from the vertex A, we go perpendicular to the base QP again. From the vertex A, we go perpendicular to the base QP. So here we can implement rule 21. Which we can rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So this is triangle ABC, side AB equals to side AC, and therefore it is an associated triangle. From the vertex A, we go perpendicular AO to the base BC. Again, from the vertex A, we go perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to this rule 21, the perpendicular AO to the base BC bisects the base BC. If BC has been bisected by the perpendicular AO, it means that it has been divided into two halves. The first half BO, of course, equals to the second half OC, and each half must be equal to BC over 2 because BC has been bisected. So BO equals to OC equals to BC over 2. So we can implement rule 21 in our drawing. When I put in our drawing, we have the associated triangle EQP. We go from the perpendicular AZ to the base QP. According to rule 21, the perpendicular AZ bisects the base QP. So the first half QZ equals to the second half ZP, and each half must be equal to QP over 2. So QZ equals to ZP equals to QP over 2. And again, the associated triangle EQP, the perpendicular AZ bisects the base QP. The first half QZ must be equal to the second half ZP. Each half must be equal to QP over 2 because QP has been bisected. So QZ equals to ZP equals to QP over 2. QP is 24. Therefore QP over 2 is 24 over 2, that is 12. And from this equation, we derive that QZ equals to ZP equals to 12. So QZ equals to 12. ZP also equals to 12. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to all the dimensions. So in this right triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this surface area must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. 90 degrees plus 90 degrees, it is equal to 180 degrees. This is the sum of the angles in a triangle. Likewise, in the swap in triangle QBS, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this surface area must be equal to 90 degrees minus alpha, according to the sum that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right triangles are similar to each other according to angle similarity rule. That is to say that this big right triangle AQZ is similar to this small right triangle QBS. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on alpha and therefore they are equal to each other. So if you found out that all the triangles of this small green triangle QBS are correspondingly equal to all the triangles of this green right triangle AQZ. And therefore, those two right triangles are similar to each other according to angle similarity rule. So, okay, now if you found out that this right triangle, the right green triangle QBS, is similar to this big green right triangle AQZ, according to angle similarity rule. And again, if you found out that the right small triangle QBS is similar, this is the sign of similar, to the big right triangle AQZ according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side SQ of this small triangle SQB or side AQ of this big triangle AQZ is equal to side QB of this small triangle SQB or side QZ of this big triangle AQZ. It again from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side SQ of the small triangle SQB or side AQ of the big triangle AQZ is equal to side QB of the small triangle SQB or QZ of the big triangle AQZ. SQ equals to 25 over AQ. AQ equals to X and this equals to QB. QB equals to A over QZ. QZ equals to 12. So in total, if you found out that 25 over X equals to A over 12. Here we of course multiply this equation. And you get that 25 times 12 is 300 equals to 8 times X. Here we divide this equation by A. And finally we get that X equals to 300 over A. have two solutions that are possible for A. The first solution for A is that A equals to 20, and the second solution for A is A equals to 15. So in the next step, we find out what is the real solution for A. Maybe it has two solutions. In order to find out what is the real solution for A, I copied this right triangle ABC with the circle that is inscribed inside it in a new drawing. We analyze the new drawing in order to find out what is the real solution for A. Okay, this is the right triangle ABC with the circle that is inscribed inside it, that I call it from the original drawing. We already found out that QB equals to A and AQ equals to X units in itself. So, we define the point of tendency of the ABC with this circle. This point is point M. We define the center of this circle. This point is point O. We define the radius of this circle as R. In the next step, we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle that equals to R. The radius OM that equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is point Q, and this is the point of tendency of tangent AB with this circle. The next step, we join points O and Q together by a straight line. OQ is of course the radius of this circle. Is equals to R, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in total, in the small quadrilateral OQBM, we have 1, 2, 3 angles, and therefore this 4 pieces angle only equal to 90 degrees in its size. According to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral QOMB we have 4 angles, and therefore it is a rectangle according to rule 5. So it's wrong. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle QOMB, side OM must be equal to the opposite side QB. But OM is out, therefore the opposite side QB must be also equal to R units in this line. So in total, we found out that QB equals to A, and QB also equals to R. QB equals to A equals to R. In the next step, we will do another construction, that is to say we'll extend the radius MO by a straight line until it touches the circle. We define the touching point of the extended radius MO with this circle. This point is point Z. When you extend a straight line by a straight line, the result is a straight line. MO is a straight line because it is a radius, We extended the straight line MO by straight line, therefore the result MZ must be also a straight line. So if you focus on the right side of this straight line MZ at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 said that the sum of the angles on one side of a straight line is equal to 180 degrees. So we check as we have the right side of the straight line ZM at point O, we have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its side according to rule 3. In the next step, we will do another construction, that is to say, from side AB of this right triangle ABC, we will go tangent to the circle at point Z. Again, from side AB, we will do a tangent to the circle at point Z. And we'll define the touching point of this tangent with side AB. This point is point T. Repeat again that TZ is a tangent to this circle at point Z according to our construction. So we have point O is the center of the circle, point Z is the point of the circle itself, and therefore OZ is the radius of this circle is equals to R. The radius of Z is equals to R. The radius of Z is 1 to point Z, that is the point of tendency Z with this circle. And whenever your radius that is 1 to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to rule 1. So in total, in the upper quadrangle TZ or Q, we have 1, 2 verticals, and therefore this fourth missing angle must be equal to 90 degrees in its size according to rule 5. So in quadrangle, the upper quadrangle TZ or Q, we have 4 rectangles, and therefore it is a rectangle. So we have in the drawing 2 rectangles, 2 small rectangles. So if you focus on the upper rectangle TZ or Q, we know that the opposite sides of rectangle are equal to each other. So the upper rectangle TZ or Q, side ZO must be equal to the opposite side TQ, but ZO is out, therefore the opposite side TQ must be also equal to R units in its length. So we only found out that QB equals to A and QB also equals to R. So write it down. We only found out that QB, line segment QB is equal to A and QB also equals to R. What is the length of this line segment or Q? Line segment AQ. AQ equals to X, according to what we already found out, but AQ consists of 2 line segments, AT plus TQ. So AQ in total equals to AT plus TQ. So it is AT plus TQ. TQ is also in total AQ equals to AT plus R. So AT equals to X and AT also equals to, again, AQ equals to X and AQ equals to AT plus R. So write it down. AQ equals to X and AQ equals also to AT plus R. AT is the length of this line segment. So AT is a length, it is absolutely a positive number. AT is a positive number, and therefore 80 plus r must be greater than r. Again, because of the fact that 80 is a positive number, 80 plus r must be greater than r. And from this long inequality, we derive that x is greater than a. Again, x is greater than a. We have those two edges. Between those two edges, we have this sign. It means that x is greater than a. So just right now found out that x is greater than a. We have two solutions that are possible for a. The first solution for a is that a equals to 20, and the second solution for a is that a equals to 15. We got the two solutions by solving the quadratic equation. Okay, so we only found out that x equals to 300 over a. According to what we already found out, x equals to 300 over a. So according to this equation, if a equals to 15, then x equals to 300 over 15, that is 20. And again, if you found out that if a equals to 15, then x must be equal to 20. Likewise, according to this equation, if a equals to 20, then x must be equal to 300 over 20, that is 15. And again, if a equals to 20, then x must be equal to 15. So x equals to 15. 15 is definitely less than 20, and 20 equals to a. So we can argue that 20 equals to a, and for this inequality, we derive that x is less than 20. X is less than 20. Actually, it contradicts our previous findings that x is greater than a. If x is greater than a, x cannot be less than. From this inequality, we learn that x is less than a. X is smaller than a. And if x is smaller than a, x cannot be greater than a. So due to this contradiction, we can set the solution that a equals to 20, a can never be equal to 20. And we left only the other solution that is possible for a is that a equals to 15. If a equals to 15, then x equals to 20. So x equals to 20. 20 is definitely greater than 15. But 15 equals to a. So we can write that 15 equals to a. And from this inequality, we learn that x is greater than a. X is greater than a. Exactly according to our previous findings that x must be greater than a. it doesn't contain this or correspondence, and therefore that is the correct answer to the question, that a equals to 15 and x equals to 20. So the length of line segment AP is equals to x is equals to 20 units in its length. Okay, this is line segment AP is equals to x, and x equals to 20 units in its length. So we finished with the second question. In the next step of some of the lecture, we start with the first question, and repeat on the solution of the first question, and then we will repeat on the solution of this question, the second question. In this first question, our task is to find out the radius of this circle that blocks quadrangle ABCD. So in the drawing, we have quadrangle ABCD that is inscribed by this circle. We know that AC is the diameter of the circle, AB equals to BC. We also know that the perimeter of this quadrangle ABCD equals to 18, that is to say the sum of its side lengths in total is 18. AB plus BC plus CD plus DA equals to 18. In addition, we know that the area of this quadrangle ABCD equals to 16 square units in its size. Again, our task is to find out the radius of this circle. So first of all, we define the side lengths of this quadrangle ABCD with letters. We define the length of side AB as A, and because of the fact that AB equals to BC in its length, therefore BC must be also equal to A units in its length. We define the length of side AD as B. We define the length of side CD as C. In the next step, we implemented the rule 7 in our drawing. Repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its side. So in the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle, and therefore it is equal to 90 degrees in its side. So according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. We can implement rule 7 in our drawing. In our drawing, we have this is peripheral angle ABC that subtends on chord AC, that is the diameter of the circle, therefore must be equal to 90 degrees in its size according to rule 7. Likewise, according to the same rule, this is peripheral angle ADC that subtends on the same chord called AC, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size according to 7. In the next step, implement the Pythagoras theorem on those two right triangles, the right triangle ABC and the right triangle ADC. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ABC, AC square equals to AB square plus BC square. And again, the right triangle ABC, AC square, that is the square of the hypotenuse, equals to AB square plus BC square. AC is the missing side, so it is. AB is A, BC is A. So therefore AB square is A square and BC square is also A square. So in total AC square equals to A square plus A square, that is 2A square. AC square equals to 2A square according to equation 1. The next step, implemented the Pythagoras theorem on this right triangle ADC. According to the Pythagoras theorem, this right triangle ADC, AC square, that is the square of the hypotenuse, equals to AD square plus DC square. Right triangle ADC, according to the Pythagoras theorem, AC square, that is the square of the hypotenuse, equals to AD square plus CD square. AC is the missing side, so leave it as it is. And it is equals to AD square. AD is B, therefore AD square is B square, plus CD square. CD is C, therefore CD square is C square. So in total, I should know that according to equation 2, AC square equals to B square plus C square. So we have two different equations for AC square. According to equation 1, AC square equals to 2A square, while according to equation 2, AC square equals to B square plus C square. Therefore, we created equation 3 that says that AC square according to equation 1 must be equal to AC square according to equation 2. AC square according to equation 1 equals to 2A square, and it must be equal to AC square according to equation 2, that is equals to B square plus C square. So in total, according to equation 3, I shall form that 2A square equals to B square plus C square. Here we divided this equation 3 by 2, and finally we all know that A square equals to B square plus C square over 2. This is according to equation 3. But according to equation 4, we found out that according to what is given in the equation, the perimeter of this quadrangle ABCD equals to 18. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is also A, CD is C, and AD is B. So in total, A plus A is 2A, plus C plus B equals to 18. So 2A plus B plus C equals to 18. According to equation 4, 2A plus B plus C equals to 18. It is also given us in the equation that the area of this quadrangle ABCD equals to 16 square units in size. Quadrangle ABCD consists of those two rectangles. Therefore, the area of quadrangle ABCD must be equal to the sum of the areas of those two shapes that it consists of. This is to say, it must be equal to the area of the first shape that it consists of, that is actually the area of the triangle ABC, plus the area of the second shape that it consists of, that is actually the area of the triangle ADC. It's given us the equation that the area of quadrangle ABCD equals to 16, and it is equals to the area of this triangle ABC. The area of this triangle ABC equals to the base AB times right BC over 2. AB is A, BC is A, divided by 2, so it is A times A over 2. So it is A square over 2, so in total, the area of the right triangle ABC equals to A square over 2 plus the area of this right triangle ABC. The area of this right triangle ABC, the area of this right triangle ABC equals to the base CD times the height AD over 2. So it is C times B over 2. Total, the area of the second shape that quadrangle ABCD consists of is equals to B times C over 2. So in total, according to equation 5, we have found out that 16 equals to A square over 2 plus BC over 2. Here we multiply this equation 5 by 2, and found out that 16 times 2 is 32, and it equals to A square over 2 times 2 is A square, plus BC over 2 times 2 is BC. So in total, according to equation 5, we have found out that 32 equals to A square plus BC. to equation 5, must be found out that 32 equals to a square plus bc. According to equation 5, we already found out that a square equals to bc, a square equals to b square plus c square over 2. Therefore, we can substitute a square in this equation 5 by b square plus c square over 2 from equation 3. We did it, and we found out that 32 equals to a square is b square plus c square over 2 plus bc. So in total, according to equation 5, we found out that 32 equals to b square plus c square over 2 plus bc. Here we multiply bc by 2 and then we divide it by 2 in order to have a common factor with this expression. So we found out over here that 32 equals to b square plus c square over 2, and we multiply bc by 2, so it is 2 times bc over 2. So according to equation 5, 32 equals to b square plus c square plus 2 times b times c over 2. Here we multiply this equation 5 by 2, and finally found out that 32 times 2 is 64 equals to b square plus c square plus 2 times b times c. Here we use the algebraic identity that says that a square plus b square plus 2 times a times b equals to a plus b square. According to this algebraic identity, we get that b square plus c square plus 2 times b times c, b square plus c square plus 2 times b times c equals to b plus c square. So b plus c square equals to 64, according to equation 5. Here we took out all of this equation, we found out that b plus c squared, the square of b plus c squared is b plus c. The square root of b plus c squared equals to b plus c, and the square root of 64 is 8. So in total, according to equation 5, we found out that b plus c equals to 8. Well, according to equation 4, we already found out that 2a plus b plus c equals to 18. And because of the fact that b plus c equals to 8, we can substitute b plus c here in this equation 4 by 8. We did it, and we found out that 2a plus b plus c is 8 equals to 18. So according to equation 4, 2a plus 8 equals to 18. Here we subtracted 8 from this equation. Equation 4, and we found out that 2a equals to 18 was 8 is 10, so 2a equals to 10. Here we divided this equation 4 by 2, and finally found out that a equals to 10 over 2, that is 5. So this is side AB, equals to A equals to 5, so AB equals to 5. Likewise, BC equals to A and A equals to 5, therefore BC equals to 5. In the next step, we implemented the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem in this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Okay, again, according to the Pythagoras theorem in the right triangle ABC, AC squared equals to AB squared plus BC squared. AC is the missing side, so we leave it as it is, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25. Plus BC squared. BC is also 5, so BC squared is BC squared. BC squared is 5, so BC squared is 5 squared, that is 25. So in total, AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. Here we substitute 50 by 25 times 2. And so AC squared equals to 25 times 2. Here we took out all of this equation and found out that AC equals to the square root of 25, that is 5, so inside the root we left only with 2. So in total, we found out that AC equals to 5 times square root of 2 units in itself. Our task is to find out the radius of this circle. The diameter AC is equals to 5 times square root of 2, and the radius must be equal to half of it. That is to say, must be equal to AC over 2. So the radius that we are looking for must be equal to the diameter AC over 2. That is to say, it must be equal to 5 times square root of 2 over 2. So in total, we found out that the radius that we are looking for in this question is equal to either 5 times square root of 2 over 2 units in itself, or in terms of numbers, the radius R of the circle is equal to 3.536 units in itself. So we finish with the first question. In the next step, I click on the solution of the second question. our task in the second question is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So in the moment we have a circle that is described by this right triangle ABC. QS equals to 25, chord QP equals to 24. This is angle ABC, this is the right angle. This is the tangent to the circle at this point. So we define the point of tendency of this tangent with this circle as SM. So SM is the tangent to the circle at point M. Again, our task is to find out the length of this line segment AP equals to x. We have to find out the value of x. So in the next step, we implemented all two in our drawing. Repeat quickly all two. Going into all two, the lengths of two tangents from a common point to a circle are equal. So in the drawing we have a circle, this is the common point P. From this common point P we have two tangents to this circle, tangent PA and tangent PB. And according to all two, all two are equal to each other. This is to say the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So we can actually implement all two in our drawing. So we put in our drawing, this is the common point A. From this common point A we have two tangents to this circle, tangent AP and tangent AQ. And according to all two, they are equal to each other. That is to say AP equals to AQ. But AP is x, therefore AQ must be also equal to x units in its length according to all two. We define the length of this short tangent VM as A. And we focus on the common point B. From the common point B we have two tangents to this circle, tangent VM and tangent BQ. And according to all two, they are equal to each other. That is to say VM equals to BQ, but BM equals to A, therefore BQ must be also equal to A in its length. SM as a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line SM at point B, the sum of the angles must be equal to 180 degrees according to all three. All three says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of SM at point B? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its side. Only two or three. The next step we focus on this common point S. From this common point S we have tangent SM. The tangent of this circle is point M. Likewise, the extended chord PQ touches point S. So all the requirements for full 10 are satisfied, and therefore we can implement all 10. Repeat quickly on all 10. According to all 10. All 10 is true in any circle, so in any circle, if LB is any chord in the circle, and PT is the tangent to the circle, then the following equation is told that PT squared equals to PA times PB, and PT squared equals to PA times PB. In the moment we have a circle, this is the common point P. On this common point P, we have tangent PT, that is tangent to the circle point T. Likewise, the extended chord BA touches point P. So in this drawing, the following equation is told that PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So, as I mentioned before, we can implement all 10 in this common point S. Why? Because we have tangent SM from the common point S, we have tangent SM that is tangent to this circle at point M. Likewise, we have the extended chord PQ touches point S. So all the requirements of all 10 are satisfied, and therefore we can implement here all 10. According to all 10, the following equation is true. That SM squared equals to SQ times SP. Again, SM squared equals to SQ times SP. And again, if we focus on the common point S, according to all 10, the following equation is true. That SM squared equals to SQ times SP. SM is the missing tangent, so SM is the missing tangent, so here this it is. And it is equals to SQ. SQ is 25 times SP. SP in total equals to SQ, that is 25, plus QM, that is 24. So in total, SP equals to 25 plus 24, that is 49. Repeat again. SP equals to 49, SQ equals to 5. So in total, SM square equals to 25, 25 times 49. Here we have to follow all the equation. We found out that SM equals to the square root of 25, that is 5, times the square root of times the square root of 49, that is 7. So in total, SM equals to 5 times 7, that is 35. So the length of this pendant SM is 35 units. What is the length from this missing answer at SB? SB equals to SM minus BM. Again, SB in total equals to SM minus BM. So SB in total equals to SM, that is 35, minus BM, that is 8. So in total, SB equals to 35 times units in its length. In the next step, we implemented the Pythagoras theorem. In this final entire SQB. According to the Pythagoras theorem, in this final entire get SQB. SQ squared, that is the square of the opponents, equals to QB squared plus BS squared. And again, SQB according to the Pythagoras theorem. QS squared, that is the square of the opponents, equals to QB squared plus BS squared. QS is 25, therefore QS squared is 25 squared, that is 325. And it equals to QB squared. QB is 8, therefore QB squared is 8 squared plus BS squared. BS is 35 on side, therefore BS squared is 35 on side squared. And total, if you found out 625 equals to 8 squared plus 300 on side squared. So 625 equals to 8 squared plus 35 on side squared. 35 on side squared equals to 45 squared, that is 1225 plus 8 squared plus 2 times 45 times 8, that is 178. So we have 625 equals to 8 squared plus 8 squared is 2 8 squared, and we have 178 plus 1225. Here we subtract the 625 from this equation. So here we left is nothing, that is to say 0, and on the other side of the equation we have 2a squared, 178, 1225 on 625 is 600. So in total, if you know that 0 equals to 2a squared, 178 plus 600. Here we divided this equation by 2, if you know that 0 over 2 is 0, 2a squared over 2 is a squared, 178 over 2 is 145a, and 600 over 2 is 300. And so if you know that a squared minus 45a plus 300 equals to 0. So actually this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared plus 4 times a times c over 2a. Now a specific quadratic equation, that is to say a squared minus 45a plus 300 equals to 0. The variable that we are looking for is of course a. So x equals to a, the coefficient a equals to 1, the coefficient b equals to 145, and the coefficient a equals to 300. All to do here, to put the data of our specific quadratic equation in this side, this general formula for x, and this way we find out the value of the values of the variable that we are looking for, that is a. So x equals to a, so substitute x by a, and it equals to minus b. B is minus 45, therefore minus b is minus 45, that is plus 35 plus minus square root of b squared. B is minus 45, therefore b squared is minus 45 squared, that is 1225. Minus 4 times a times c. A is 1, c is 300, so minus 4 times a times c is minus 4 times 1 times 300, that is minus 1200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, if we found out that a equals to 35 plus minus square root of 1225 minus 1200 over 2. 1225 minus 1200 is 25. So in total, if we found out that a equals to 35 plus minus square root of 25 over 2. The square root of 25 is 5, so in total, if we found out that a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for A is that A equals to 35 plus 5 over 2. 35 plus 5 is 40 and 40 over 2 is 20. So if we found out that the first solution for A is that A equals to 20. The second solution for A is that A equals to 35 minus 5 over 2. 35 minus 5 is 35 minus 5 is 30. 35 minus 5 is 30 and 30 over 2 is 15. So the second solution for A is 15, the first solution for A is 20. In the next step, we focus on this ring triangle AQP. The ring triangle AQP is an associated triangle because AQ equals to AP. QP is of course the base of this green associated triangle AQP. From point A, we do perpendicular AZ to the base QP. Again, from point A, we do perpendicular AZ to the base QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So here we can implement rule 21. And since we can rule 21, according to rule 21, the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. In the moment, we have triangle ABC. Side AB equals to side AC, therefore triangle ABC is an associated triangle. BC is of course the rest of this associated triangle, triangle ABC. From point A, we do perpendicular AO to the base BC. Again, from point A, we do perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to this rule 21, the perpendicular AO bisects the base BC. Again, the perpendicular AO bisects the base BC. If BC is been bisected, it means that the first half BO must be equal to the second half OC, and each half must be equal to BC over 2. So BO equals to OC equals to BC over 2. So I'm going to implement rule 21 in our drawing. When I put in our drawing, we have the perpendicular AZ, according to rule 21, the perpendicular AZ to the base BC, the perpendicular AZ to the base QP bisect the base QP. That is to say QZ, the first half QZ must be equal to the second half ZP, and each half must be equal to QP over 2. So according to rule 21, the perpendicular AZ bisects the base QP. The first half QZ equals to the second half ZP, and each half must be equal to QP over 2. QP is 24. Therefore, QP over 2 is 24 over 2, that is 12. From this equation, we know that QZ equals to QP equals to 12. QZ equals to 12, and ZP also equals to 12. Those two angles are defined as vertex angles, and you know the vertex angles are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the order dimensions. So in this big triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in any triangle. Likewise, this small great triangle SQV, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. The next step we prove that those two right great triangles are similar to each other according to angle similar to. That is to say those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the three angles of this right triangle SQV correspond equal to all the three angles of this right triangle AQZ, and therefore those two right triangles are similar to each other according to angle similar to. And again, if you found out that this whole triangle SQV is similar to the big triangle AQZ according to angle similar to. And so we found that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side QS of this green triangle QBS or side AQ of this green triangle AQZ is equal to side QB of this green triangle SQB or side QZ of this green triangle AQZ. We derive from the fact that those four triangles are similar to each other. We derive that the following relationship exists between their sides. We derive the side SQ of the small triangle SQB or side AQ of the big triangle AQZ is equal to side QB of the small triangle SQB or side QZ of the big triangle AQZ. SQ is 25, AQ is X, QB is A, and ZQ is 12. So, in total, if you found out that 25 over X equals to A over 12. Here, of course, multiply this equation. If I found out that 25 times 12 is 12, and 25 times 12 is 300, and 300 equals to 8 times x. Again, 300 equals to 8 times x. Here we divided this equation by a, and if I found out that x equals to 300 over a. So, we have two solutions that are possible for a. A could be equal to either 20 or to 15. In order to find out what is the value of a, we copy this right triangle ABC with the circle that is inscribed inside it, in a new drawing, and analyze the new drawing in order to find out what is the real value of A. So this is the right triangle ABC with the circle that is inscribed inside it, and the code from the original drawing. We only found out that AQ equals to X and QB equals to A. So here we define the point of tendency BC with this circle, this point is point M. We define the center of this circle, this point is point O. We define the radius of this circle as R. In the next step, we join points O and M together by side line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that equals to R. The radius of M that equals to R, the radius of M is drawn to point M that is the point of tendency BC with this circle. And whenever your radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Point Q is the point of tendency AB with this circle. So in the next step we join points O and Q together by side line. OQ is of course the radius of this circle, that equals to R, and according to rule 1 this angle equals to 90 degrees and this angle also equals to 90 degrees. So in the small quadrilateral Q, O, and B we have 1, 2, 3 degrees, and therefore this fourth missing angle must be equal to 90 degrees inside according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral Q, O, and B we have 4 degrees and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle Q, O, and B, side OM must be equal to the opposite side QB. But OM is R, therefore the opposite side QB must be also equal to R units in itself. So in total QB equals to A and QB also equals to R. In the next step we did the construction, that is to say we extended the radius OMO by side line until it touches the circle. We define the touching point of the extended radius MO with this circle, this point is point Z. MO, it is a radius. It's a radius, it is absolutely a straight line. When you extend the straight line by straight line, the result MZ must be also a straight line. So MZ is a straight line. If you focus on the right side of the straight line, MZ is point O here. The sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angle we have the right side of the straight line ZM at point O, we have this angle that is right angle, plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in size. In the next step, we did another construction, that is to say from side AB, on the triangle ABC, we draw tangent to the circle at point Z. Again, from side AB, we draw tangent to the circle at point Z. We define the touching point of the tangent with side AB, this point is point T. Again, TZ is a tangent to the circle at point Z according to our construction. Okay, again, TZ is a tangent to the circle at point Z according to our construction. Point O is the center of the circle. Point Z is the point of the circle itself. Therefore, OZ is the radius of the circle that equals to R. The radius OZ is equals to R. The radius OZ is drawn to point Z, that is the point of tendency Z with this circle. Now, your radius is drawn to the point of tendency, then tangent Z will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to rule 1. So in total, in the upper quadrant of TZOM, we have 1, 2, 3 rectangles. And therefore, this fourth piece again must be equal to 90 degrees in size. So it has 4 rectangles, this upper quadrant, TZOM, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle TZOQ, side ZO must be equal to the opposite side TQ, but ZO is out, therefore TQ must be also equal to 1 unit in its length. We found out that QB equals to A and QB also equals to R. And QB equals to A, QB also equals to R. What about AQ? AQ from one side equals to X. But AQ consists of 2 line segments, AT plus TQ. So AQ must be equal to AT plus CQ. So AQ total must be equal to AT plus CQ. That is R. So in total, AQ equals to AT plus R. So AQ equals to X and AQ also equals to AT plus R. AT is the length of this line segment. AT is a length, it is absolutely a positive number. And therefore AT plus R must be greater than R, because AT is a positive number. Again, AT plus R must be greater than R. And from this Lorentz inequality, we will derive that X is greater than A. Again, X is greater than A. X is greater than A. Okay. So, we just right now found out that X is greater than A. We have 2 solutions that are possible for A. A could be equal to either 20 or could be equal to 15. We only found out that X equals to 300 over 8. We can write here that X equals to 300 over 8. So according to this equation, if A equals to 15, then X must be equal to 300 over 15, that is 20. So if A equals to 15, then X must be equal to 20. Likewise, according to the same equation, this equation, if A equals to 20, then X must be equal to 300 over 20, that is 15. So if A equals to 20, then X must be equal to 15. So X equals to 15. 15 is definitely less than 20, and 20 equals to A. Again, 15 is less than 20, and 20 equals to A. And from this inequality, we derive that X is less than A. X is less than A. X is smaller than A. It contradicts our previous findings that X must be greater than A. If X must be greater than A, X cannot be less than A. So due to this contradiction, we consider the solution that A equals to 20. A can never be equal to 20. And we take into account only another solution for A, that A equals to 15. So if A equals to 15, then X equals to 20. So X equals to 20. 20 is definitely greater than 15. Again, 20 is definitely greater than 15. It equals to A. 15 equals to A. From this inequality, we derive that X is greater than A. Okay, X is greater than A. Exactly according to our previous findings, that X must be greater than A. So the answer to the question is that line segment AP is equal to X is equal to 20 units in its length. Okay, again, this is line segment AP is equals to X, and X equals to 20 units in its length. Okay, thank you very much.